Good afternoon and welcome to the Radar Rainfall Calibration webinar. Thank you for joining us. The webinar today will be led by Steve Clark and Alan Seed from the Bureau of Meteorology, Steve from Water Technology. The first part of the presentation will have Alan talking about the radar components, and Steve will then bring that together with a case study and also a bit of an explanation on how the HydroNET platform can use the radar data. Alan, working for the Bureau of Meteorology, is not here to as an endorsing of anything that we're doing, but to provide some clear background as to radar technology that's available within Australia, as somebody that's got incredible experience and expertise in this space to provide an element of confidence in what we're doing with this type of data. My name's Luke McPhail, and at the end of this webinar we're going to be having a time for some questions and answers. If you have questions as we move through, you are welcome to type them into the chat component. It is at the end that we're going to be able to get to those, so we can make sure that we cover the content that everybody is seeking. If we are not able to cover your question at the time, we will get back to you after the webinar to provide answers to your questions. And with that, I'll just provide a little bit of background introduction to Alan and Steve. Alan Seed is a Principal Research Scientist at the Bureau of Meteorology and the Adjunct Professor at the University of New South Wales. He's educated in South Africa with a Bachelor of Science in Civil Engineering and a Masters of Agricultural Engineering, and has completed his PhD with a thesis on radar rainfall statistics through McGill University in Montreal, Canada. He's worked in South Africa on water resource and flood warning projects, and at the Auckland University's Physics Department as a postdoctoral research fellow on orographic rainfall, before coming to Melbourne and joined the hydrology unit at the Bureau of Meteorology. Alan started work on developing weather radar applications in 1985 while still in South Africa, and has worked on developing operational systems for radar rainfall estimation and forecasting that can be used for hydrological applications since then. He works in radar science and nowcasting team in the research and development branch at the Bureau, and manages the science and engineering section in the observations and infrastructure division. His research interests include stochastic modelling of rainfall in space and time, radar rainfall estimation, and using radar data for very short-term rainfall forecasts. He leads a team of scientists and software engineers who are responsible for developing and maintaining the operational radar, rainfall estimation and forecasting software, and a range of data visualization applications. As a manager of science and engineering, he leads the engineers and technicians who develop and install the Bureau's observation infrastructure. Steve Clark has more than 25 years experience as a specialist in water resource and coastal engineering fields, specialising in flood risk and flood risk management. He's an honours degree in engineering and Masters of Engineering Science from the University of Queensland. Steve is one of the founding directors of Water Technology and has been the Director of Water Technology's Brisbane office since 2006. Steve's been involved in a variety of work projects, including waterway, floodplain and floodplain risk management, infrastructure investigations, and frequently utilises advanced hydrodynamic modelling systems, and has been undertaken throughout Australia and internationally. Notably, a number of projects, including in the Yangtze River in China, through Samoa, to do with following reconstruction efforts after the tropical cyclone Evan, and also to help develop better planning outcomes. I'll now hand over to Alan, and Alan's going to talk through the radar work. Alan, I think you might still be on mute. So Alan's just sharing his screen at the moment. Welcome, Alan.
Okay, thank you. Thank you for the invitation to talk at this webinar. As you heard from my bio, this is something radar rainfall estimation is something that I've been working on since 1985. And for me, the primary motivation for spending this time and energy on radar rainfall is to build a system that is good enough to be used operationally for hydrological prediction and water resource management. And I think finally, after about 30 years of effort, we're pretty close to getting something that I'm really proud of and I believe is useful and usable in operationally for hydrology. So this for me is always a great pleasure to talk about the Rainfields application. Rainfields itself started to get developed in the Bureau in around 2000. In 2010 we rewrote it in Rainfields 2, and then in 2015 we redeveloped it, started redeveloping it in Rainfields 3. And we're now in the final stages of acceptance testing to get Rainfields 3 deployed operationally at the Bureau. And this is what I'm going to talk about today, is the next generation of our Bureau radar rainfall estimation scheme. So the Bureau runs a network of 58 radars. Not all of them are capable of generating, not all of them have the quality that's needed to support quantitative radar rainfall estimation. And so out of the 58 radars, we have 50 radars that we use for radar rainfall estimation. On the screen there is the complete network, and at the moment these 3 radars are in the process of being installed, and this Newdigate radar came online operationally a few months ago, and the next 2 new radars will be online before the June of next year. The other big activity that's happening in the Bureau at the moment is that the high range radars, the top of the line radars which we use in Adelaide and Melbourne and Sydney and Brisbane, the 1 degree S-band radars are being upgraded next year to the latest technology. So this will mean that we take the radars offline for 3 to 4 weeks, and we replace the radar receiver and we upgrade the technology to the latest international standard for these types of radars. So we're very pleased that we are still able to advance the quality of our network. So this is more or less the theoretical coverage of our radar network, and one of the outstanding features of the radar network is that there's a wide range of radars. So some radars are 30 years old and others have been deployed a few months ago. And within that there's a wide range of technology and capability. So the next, what I have here is the coverage. So on the left hand side is the map of Australia with the coverage. And this is a radar quality index map where blue is good and green is useful and yellow is qualitative only. Just to give you an idea of the areas, actual areas that are covered by radar in Australia. So it's 97%, I think, of the population is covered with radar, but the area of catchments, the important catchments, is much less. And so this is one of the issues we face is radar coverage over the catchments that hydrologists typically care about. On the right-hand side is a map of the 1,700 real-time rain gauges that the Bureau has at its disposal at the moment. And there, once again, blue is adequate coverage, and yellow is qualitative coverage only. So if you get too far from a rain gauge, you more or less don't know what the hourly rainfall is going to look like. So you can see immediately the advantage of radar is that it has actually, although it's limited spatial coverage, it's much, much better than the coverage that you would get from a set of rain gauges, unless you've gone out yourself to put in rain gauges for a specific catchment. Rainfields itself is an application that takes in the data from the 50 radars. It takes in the 1700 real-time rain gauges, the 30-minute rainfall accumulations from the rain gauges, and it takes in a fair bit of information from the numerical weather prediction models. And these data come into the Bureau and are fed into an application that we run at the head office itself and also in our disaster recovery site. So it's a centralized processing system. And Rainfields undertakes the quality control of the radar data. It then converts the data into the radar observations into rainfall estimates, and then progresses to make the estimates into very short-term forecasts. It actually generates around 10,000 products an hour. It's really, when you look at the number of individual products and there's 50 radars, so it's really, you get the impression that you're sitting at the wrong end of a fire hose when you're looking at all the data that comes out of this thing. There's several terabytes per day of forecasts. And the people who use these data operationally at the moment are the Bureau weather forecasters. Some of the data are used as the rainfall pages in the public weather web pages. Some of it is used as starting for the numerical weather prediction, and increasingly our hydrologists are bringing online systems that can use the radar data operationally for their flood forecasting and hydrological prediction. Rainfields itself has an extensive suite of quality control algorithms, because the fact of the matter is that not every echo that comes back on a radar is a raindrop. So we have to do a lot of work to clean the fields and examine and find exactly where's the rain and where are the echoes from trees and buildings and ships and other targets. Some of the issues we have to deal with is that the topography blocks some of the signals, especially when we're scanning close to the horizon. And so we have algorithms based on high-resolution elevation models to predict how much blockage is taking place with a particular radar scan. And so we know where it's blocked, and we can do some partial corrections where the blocking is not too bad. We also keep a climatology of the echoes, excuse me, and this helps us understand where are there permanent echoes due to mountains and where are there permanent holes where the radar has identified mountain echoes and consistently removes them before we receive the data. Of course, we know what the topography is, we know where the coast is. So when we're looking for sea clutter, we only look for it on the sea. When we're looking for mountain returns, we only look for them in the mountains, trying to add intelligence to the algorithms that we do. Some of the major things are quality control and reflectivity to remove the clutter. So you can see from here is a raw field that comes in from the radar. And on the right-hand side, we've now removed things like this light blue area here. These are echoes from insects. We have echoes from mountains. We have a range of things. So we have to identify where the echo is coming from. And then once we've done that, we can remove the echoes that aren't rain and just leave the echoes from the rain that we can then convert into our systems. And a similar thing for the radial velocity, or the wind speed that we can get from our Doppler. This is not so much of interest to hydrologists, but it's of enormous interest to our numerical weather prediction people who use these observations of wind speed for their numerical weather prediction systems. And then we have, after we've done quality control, we then convert the data into a rainfall estimate. And we have a real-time spatially distributed bias correction. So each rain gauge in the field has a Kalman filter applied bias correction, which we then use kriging to distribute in space. We blend the data with the observations for the 30-minute gauge accumulations using conditional simulations. And then we provide products which would be accumulations and forecasts. So the products then is quality controlled radar data, the radar reflectivity. Then we convert that to an estimate of reflectivity on the ground, so we can convert that into rainfall. And then we have algorithms to convert radar observation into rain rates. And then we do the accumulations and then once we have the accumulations, we can then do the forecasts. And in the forecast space, we have two types of forecasts. The first is a longer range 0 to 12 hour forecast. And what this does is takes the radar rainfall estimate and then blends it into the numerical weather prediction to give us a 12-hour forecast. And this gets updated every 10 minutes with the next radar image, and it's good for over a 500 kilometre domain over Melbourne, Sydney and Brisbane. And the other product we have is a radar-only product, so it's a 0 to 90-minute forecast. It gets updated every 6 minutes, and it runs out to 90 minutes, and we do that for each of our 50 radars in Australia. So the key requirements that we had for our Rainfields 3 is it had to be flexible. It had to take into account the different characteristics of the different radars. It had to be scalable, so we needed to be able to process 50 radars in parallel. It needed to be responsive. If you only got 6 minutes to complete everything, then you have to be aware of not having spending time where it's not necessary. So we're under enormous time pressure because the radar runs at a 6-minute time, and we have to keep up. We have to complete everything within 6 minutes. And finally, what's very important is that the data need to be accessible so that end users can find the data, they can subscribe to data feeds, that they get the data in standardized products and formats, so that when they receive something, they can start to use it immediately without first learning some arcane or inappropriate format. So these were the main design criteria. It had to be flexible, scalable, it had to be low latency, and it had to be accessible. So this is a technical thing. I'll just put it in there to show you that for each radar has its own characteristics. So we have a separate suite of quality control algorithms that we can stitch together for each of the radars. And the system has been designed so we can take a specific algorithm, we code it up in C++, and then we can configure that specific radar to perform that specific algorithm in a flexible way. And this is quite unique in Rainfields 3. To give you an idea of the quality control, what we have on the left is a raw radar image, and what we have is a series of thunderstorms out to sea, it turns out. What's happening here is that we're close to the radar, we can see lots of insects, and this is the low reflectivity. And these echoes in this area are actually ground echoes, and what's happening here is that there's a strong gradient of temperature and humidity in this area, and the radar beam gets bounced back from the atmosphere back onto the ground in this area. So you think you're observing at some height above the ground, but the reality is that you're actually observing on the ground. And so you can see that there's a number of quality control issues that you have to address and clean, because if you were to feed your hydrological model with this kind of echo, you'll be getting significant stream flows, and it's really just clutter and not rain at all. So it's very important for us to spend the energy and effort on getting clean data and identifying very carefully what's rain and what's not rain. So here we have the classification. We have rain, we have clear air, insects, and then this is the dark green is where we have this anomalous propagation. This purple is another class of clutter, and so in the end it's the blue which we use for our rainfall estimations. And we also have to clean the Doppler data and clean it from its artifacts. The other thing we do is actually track all the echoes in real time, and this shows you some streamlines of the motion of the field as rain moves over Melbourne. So we can see the streamlines, and so what we do then is we track the field using an algorithm that was developed for robots, and this allows us to simulate 1 minute data when we make our 6-minute accumulations. We also use it to correct for the different timestamps of the various radars. Some of them run at 6 minutes, some of them at 10 minutes. And of course we use these advection fields to make our nowcasts, short-term 0 to 90-minute forecasts. It's very important for the end users to understand the quality of the data, and we have developed a novel technique to understand what is the quality of the radar product at any location in real time, because the radar that is dependent on observing the rain, and on cold days the rain tends to be shallow, so it only extends maybe 3 or 4 kilometers up above the ground. And on those days when it's shallow, then the range of the radar is limited, because the radar starts to overshoot the top of the clouds, and so you just don't know what's happening underneath the radar at a certain distance. And also we need to know where's their blockage from hills and mountains, and where's their clutter that we just can't see because of the ground clutter. So what this shows you is a map, and the pale colors are, this is error, this is the error terms, so the pale colors are low errors and the blues are significant errors. And this is updated every 10 minutes as the temperature changes and as the characteristics of the rainfall change. We also have a real-time bias adjustment scheme that gets updated every 30 minutes. So on the left we have a set of images from Melbourne again, and then on the right-hand side we have the adjustment factors that we use to correct the radar data for each of these images. And you can see at the far range in the Melbourne radar, at this far range here on the Alps, because of the range and because this is rain in the mountains, there's a systematic underestimation of radar rainfall from the Melbourne radar at this location. And in these areas here, you would multiply the raw rainfall that comes from the radar by a factor of 1.2, 1.3, something like that. So we adjust the radar in real time spatially based on the observed biases that we get from our rain gauges using appropriate filters, Kalman filters, some sophisticated geostatistics to get the field done appropriately. So we've gone to some trouble to get a real-time adjustment of our rain gauges feeding into our radar estimation products. The other thing that's important for end users is the verification statistics. And so we've gone to considerable lengths to understand for ourselves what is the quality of our product, and then also to monitor it and track it in real time so we can understand, is the calibration of the radar itself drifting? Is there an issue with the radar hardware? Is there an issue with our algorithms on particular days? So we can go through and have successive improvements over time as we learn the performance of our algorithms. So we base it on the 30-minute gauge versus the 30-minute radar, and then we're in the process now of also developing the daily radar versus the daily rain gauges. So this is an independent set of rain gauges. We look at four lengths of windows of statistics: the last 7 days, the last 30 days, and out to the last year. And generally in Australia, nothing much happens in a week. Very often it doesn't rain for a week. So we find that with verification, we need the last 30 days or the last 120 days in order to get enough observations to make have a clear idea of the current characteristics of the radar. This is just one example from Melbourne, I think. So what this is the logarithm of the gauge divided by radar. Gives you an idea of the mean bias of the field, and you can see how it tracks from day to day, and you can see that this is the expected value, the mean value, and these are the upper and lower limits for individual rain gauges on each of those 30-minute time steps. So we use this to monitor the quality of radar and to see how things are going in real time. We go now to what sort of products do we make. So Rainfields 3 has evolved to make mosaic products. So Rainfields 2 was very much radar centric, so we would only produce products for individual radars, whereas now we're starting to produce multi-radar mosaics over regional areas. So this is an example of the southwest corner around Perth. These are the radars in the southwest corner. And this is the mosaic field. And we use these error maps to inform us as to what are the weights that we use from individual radars when making up a mosaic. So we now have a national mosaic of radar rainfall. So that's quite independent of individual radars. We have these mosaics for all the accumulation periods, and we can actually serve a field of national rainfall. But you have to understand that national in the sense that it's all the radars, but there's many areas that aren't covered by radar. Typical products are like the 60-minute accumulation over the last 60 minutes, the accumulation since 9 a.m., and then we do a range of forecasts. So in summary then, Rainfields 3 is our next generation operational radar rainfall estimation and nowcasting system. It's in its final stages of testing and being transitioned onto operational computers, and this will be complete certainly by July 17. It takes a while to be completely certain that an operational system is ready for deployment, so we run it in parallel with Rainfields 2, and we'll do the switch over by July. It manages all 50 radars, whereas Rainfields 2 only managed 20 radars. It generates the forecasts, which is the STEPS algorithm, we call it STEPS, which stands for Short-Term Ensemble Prediction System. And this generates a 30-member nowcast ensemble for each of the radars and for the multi-radar mosaics. And we generate 10,000 products an hour, so it's a major system. It produces a wide range of products, and we've gone to some trouble to understand its quality and to report its quality in real time. Thank you.
Thank you, Alan. I must say I found that incredibly interesting.
Fantastic. Thank you, Alan.
You can go, Steve.
Sorry, Luke, we're talking over each other. Thank you, Alan. It's fantastic. It's a great opportunity for everybody to get an update on where things are at. In particular, the upgrade to the Rainfields 3 product is very exciting. So if I can work the technology here,
I'll hand back my. Are you done it?
There we go. Transfer over to how the radar rainfall products can be used within the HydroNET platform. I'll give you a brief overview of some of the work we've been doing more at an applied level here at WaterTech, and then give you a demonstration as to how these products can be accessed. So again, if I can move forward. So clearly the problem in a continent as large as Australia is that we can't afford to have rainfall gauges at the density that we would like them, and this is an ongoing source of frustration for I'm sure all concerned, all listening in, and it as a response to that, we some years ago started investigating how we could augment the rainfall gauges, because as everybody here knows, they're never enough for what you want. Of recent times, we've been doing a lot of case studies using the Rainfields dataset as previously described by Alan. I'm going to talk in particular, or I'm going to present in particular the work of Greg Hansel, one of our engineers here, but also there was a large group of people contributed to this investigation that looked at the use of calibrated radar rainfall in what we would normally consider to be a flooding investigation. Greg presented these results at the 21st Queensland Water Symposium in 2016. There will be a more detailed presentation, just as an advert, in the FMA conference coming up next year. So, in particular, following the 2011 rainfall events, there was a lot of discussion about rainfall that had fallen in between gauges. There was a lot of difficulty in calibrating models, and so we have looked at three broad areas, and one area in particular that I'll give you the results of those investigations for. There's been a lot of work done up in the Stanley River, but also in the Lockyer Valley, and in particular Murphy's Creek, and it's the Murphy's Creek example that we'll talk through here today. This is part of a thesis project undertaken by Chris Delaney. I think people are probably well aware of the events in late 2010, 2011 in Queensland, where there was some extreme rainfall, and the events in particular of January 2011 in the Lockyer Valley. There is limited information, and certainly limited rainfall gauging information in this particular area that work into that is available. Now, one of these gauges is incorporated in the radar dataset, but there are other gauges as well. But there are clearly difficulties calibrating these models to match observed data. So, what the example that really made this stand out to us is the rainfall surfaces, the cumulative rainfall surfaces that you get when you compare interpolated rainfall gauge information with what the Rainfields data set provides you. So you have here two plots. On the left is the interpolated surface based on rain gauges, and on the right the interpolated surface, or sorry, not interpolated, the calibrated radar data information out of the Rainfields data set. The areas to look at are in the vicinity of Murphy's Creek up in here. So the green at the scale and with these colourings, it shows less rainfall than the yellow data sets over here. The green is 250 to 300 millimetres, the yellow is 300 to 350. So if we look at that in a little bit more detail, this is a plot of the Murphy's Creek catchment showing the difference between those two surfaces. So you have one rain gauge at the top of the catchment, and so at the top of the catchment it's more or less the same. And then as you move across to the eastern side of the catchment, you've got radar totals that are showing some 60 millimetres higher than the interpolated surfaces based on rain gauges. So what does that mean when you put it into a hydraulic model to look at the impacts on flows? So the black curve here is the gauged flow. We have to say that the gauge did fail during this event. So the accuracy of the peak, there's some uncertainty about it, but clearly a significant event was experienced. If you feed the rainfall surfaces based purely on interpolated rain gauge information through that model, you get a blip. You effectively don't pick up anything like the magnitude of the event itself. Whereas if you use the calibrated radar model, you get this red curve here. Clearly there is some discrepancy here. There could be multiple reasons for that discrepancy, but this was the example that really highlighted to us the stark difference where interpolating on rain gauge surfaces, you could effectively miss flood events that the Rainfields data set effectively gives to you. So there's we're quite excited from the point of view of there's another data set here with some radar where you have radar coverage, which can potentially give you a really valuable additional data set on top of your rain gauges that will really